Hello students, welcome to today's class. In today's class, we are going to talk about how to design a type 1 bracket connection. So that's what we are going to check down in our today's class. So the question is design a bracket connection to transfer an end reaction of 300 kilonewtons with an eccentricity of 170 mm. And the steel is used of grade Fe410 using M20 bolts of grade 4.6. The thickness of bracket plate is 10 mm and the column section is ISHP 200. So this is the data that is provided in the question. So what they are telling, so you have to design a bolted bracket connection where it has to transfer an end reaction of 300 kilonewtons, and this 300 kilonewtons is acting at an eccentricity of 170 mm, and the thickness of bracket plate is 10 mm and the column section is of ISHP 200. So this is the data that is given in the question. Now by seeing the data, the diagram can be drawn in this way as shown in the figure. Okay, a steel plate, that is a bracket plate, is connected to a column, that is ISHP 200, and the load is acting, that is 300 kilonewtons of load is acting at an eccentricity of 170 mm from center of the column section. Now let's design the section. So the solution can be written as, initially we have to write the given data. So given data. So the load value is given as 300 kilonewtons, load P equals to 300 kilonewtons, and eccentricity is denoted with small e. Eccentricity is given as 170 mm, and the diameter of bolt is M20 bolts. So for M20 bolts, diameter of bolt D equals to 20 mm, and to provide 20 mm bolts, we need to provide a bolt hole of 22 mm diameter. So this is the 22 mm diameter bolt hole, and the thickness of bracket plate is also given, which is 10 mm, that is thickness of bracket plate is given as 10 mm. Okay, so here the grade is also given, which is 4.6. So for 4.6 grade, the value of FUB, which is ultimate bearing stress, is 4 times of 100, that equals to 400 megapascals, and the value of FYB is 400 times of 0.6, that equals to 240 megapascals. So this is the data that is provided in the question, right? And also they have given the section which is ISHP 200. So for this section, we have to write down the properties of section. So from steel tables, the properties of ISHP 200 at the rate 365.91 Newton per meter are, so let's write down the properties of ISHP 200. So we have to write down the area, we have to write down the width of flange, the thickness of flange, thickness of web, and the gauge distance, that is G. So by seeing the code book or by seeing the steel tables book, you can write down all these values. So for time being, I'm writing the values of ISH, that is thickness of flange, that is 9 mm, and the gauge distance for ISHP 200 is 100 mm. So you can write down these properties, the rest of the properties, that is area, width of the flange, and thickness of the flange as well, right? So this is the data that is provided. Now let's solve the problem. So the first step is design strength in shear. So this is the first thing which we have to solve. Design strength in shear, that is VDSB equals to VNSP by gamma MB. So let's solve for this. VDSP equals to VNSP formula is FUB by root 3 NN plus NS ASP into 1 by gamma MB. Okay. Now here if you check down, the type of joint given is a lap joint. So it's a lap joint. So how I am able to tell it as an lap joint is, so a column section is there. This is the column section. It is ISHP 200. On the column section, we are overlapping the bracket plate. So this here you are technically doing a lap connection. So for lap joint, the value of NN is taken as 1 and the value of NS is taken as 0. So remember, for lap joint, the value of NN is taken as 1 and the value of NS is taken as 0. Now, therefore, VDSP equals to FUB value is 400. So we have solved here 400 upon root 3 into NN. NN value is 1. A and B formula is 0.78 pi by 4 into D square, where D is the diameter of bolt. So the diameter of bolt here is 20 mm. So you can check down. So the diameter of bolt is 20, that is 0.78 pi by 4 into D square, plus NS value is 0 and ASB formula is pi by 4 into D square, where again D is the diameter of bolt, into 1 by 1.25. Gamma MB value is 1.25. So if you solve for this equation, the VDSP value is obtained as 45.26 kilonewtons. So this is how you can find out the value of VDSP. Now let's find out the second value, that is design strength in bearing. Design strength in bearing. So this is the second value, that is design strength in bearing. So the design strength in bearing formula you know, which is VDPB equals to VNPB by gamma MB. VNPB formula we know, however. So VDPB equals to VNPB formula is 2.5 KB D T into FU into 1 by gamma MB. Now here, in order to find out the value of KB, okay, so in order to find out the value of KB, KB is the least of, we have 4 values in order to find KB value. One is E by 3D naught, second one is P by 3D naught minus 0.25, third value is FUB by FU, and fourth value is 1. So among all these 4, that is E by 3D naught, P by 3D naught minus 0.25, FUB by FU, and 1. So among all these 4, whichever is the least value, that you are going to take as KB. Now here, the edge distance and pitch distance values are not provided in the question. So if you check down in the question, they did not talk about the edge and pitch distances. So as per IS 800-2007, the minimum edge distance to be provided is 1.5 into D naught, and the minimum pitch distance to be provided is 2.5 into D. So 1.5 into D naught is E equals to 1.5 into D naught, where D naught is diameter of bolt hole, which is 22 mm. So 22, and the P value equals to 2.5 into D, where D is the diameter of bolt, that is 20. So 2.5 into 20 will give you approximately 60 mm pitch. Okay, so P equals to 60 mm, and the edge distance you will get it as 33 mm. So approximately you assume it to the nearest value, that is 40 mm. So now we have got edge and pitch distances. So if you substitute the values of EP values, then you can get the least value of KB. FUB value, remember FUB value we have solved already, which is 400 newtons per mm square, and FU value is fixed, which is 410 newtons per mm square. So you just substitute the values and find out. So the least value of KB is obtained as 0.6060. So this is the least value of KB, which which you will get after solving all the four values. So therefore, VDPB equals to 2.5 into KB. KB value is we know, which is 0.6060. So now 2.5 KB dt into FU. So 2.5 KB value is 0.6060. D is the diameter of bolt, which is 20. And the T value we don't know. For time being, let us keep the T value aside. And FU is 410. Now, here we need to take the value of T. So T is the least thickness of, so the value of T is considered as the least thickness of two conditions. First one is thickness of bracket plate. So this is first condition. So the thickness of bracket plate is given in the question, which is 10 mm. So the thickness of bracket plate is given in the question. So that is 10 mm. And the second condition is the thickness of flange of ISHB section. So thickness of flange of ISHB section is obtained from steel tables book. So the thickness of flange of ISHB section is 9 mm. Okay, so now you have got 9 mm as the thickness of flange of ISHB section. So 9 mm. So therefore, the least value of thickness section is either 10 mm or 9 mm. So in these two, whichever is the least value, that you have to adopt here. Okay, that's how you can calculate the value of T into 1 by gamma MB. Gamma MB formula is 1.25. So therefore, upon solving, the value of VDPB, the value of VDPB is obtained as 88.8 kilonewtons. So this is how you can calculate the value of VDPB. So here the remembering factor is the value of T consideration. So the value of T is the least thickness of bracket plate and thickness of flange of. So now you have got the VDPB value. Now we need to know the design strength. So design strength equals to, so we know how to find out the design strength value. It is the least of VDSB and VDPB. So this is how you can calculate the design strength value. So the least of VDSB is design strength is one, we have got 45.26, and the second value we have got is 88.8. So therefore the design strength will be 45.26. So now you have got the design strength value as well. So far we have calculated the values of VDSB and VDPB. Now let's find out how many number of bolts are required for this connection. So here, why to find out how many number of bolts? Because you need to connect bracket plate with the column section. So this bracket plate has to be connected to the column section. So let's find out how many number of bolts are required. So I'll write here. So third step is number of bolts required. So number of bolts required. So the formula is N equals to under root 6m divided by P into N dash into VSD. It is VSD. Okay, so here it is M, which is moment. So this is the formula to find out the number of bolts. Now here, moment M equals to force into perpendicular distance. This formula we know. So force into perpendicular distance. What is the force? We have force which is 300 kilonewtons and perpendicular distance is this one, that is 170. So force is 300 and perpendicular distance. So kilonewtons to newtons, perpendicular distance is 170 mm. So therefore, you can find out the value of m. And here P is pitch distance or pitch. So the value of pitch which we have adopted is 60 mm. So you can check down here, P value. So 60 mm. And N dash is number of rows of bolts. So N dash is called as number of rows of bolts. So for type 1 bracket connection, you need to provide at least 2 rows of bolting. This is the minimum value. So I am adopting N dash value as 2. That is number of rows of bolts is adopted as 2. And VSD is the design strength value. So VSD is the design strength value. So we have got design strength, which is the least of strength in shear and strength in bearing. That is 45.26. 45.26 kilonewtons. Now substitute all the values of the formula of N. So you will get N value as approximately 7.5. So therefore adopt 8 bolts. So therefore provide 8 bolts in each row. So how many rows we have? 2 rows. So 2 rows means 16 bolts. 8 into 2 will give you 16 bolts. So we are providing 8 bolts in each row. So therefore, on a whole, the total number of bolts required for the connection are 16. That's how you can find out the values of number of bolts. Now let's find out the force values. So here in bolts, we have 2 types of forces. The first one is direct shear force. This is one value, that is direct shear force. So the direct shear force is denoted with the symbol F1. F1 equals to, there is a fixed formula which is load by N, where N is number of bolts or the total number of bolts. F1 equals to, we know the load value, which is 300, right? That is what they have given, 300 kilonewtons. And the number of bolts in the connection are 16, the total number of bolts. So here N is total number of bolts. So this is how you can find out the value of F1. So F1 value is obtained as 18.75 kilonewtons. So now we have got F1 also. Now the second force which is acting on bolt is the torque force. Torque force. Torque force, the formula is F2 equals to PERN by summation of R square. So this is the formula to find out F2, which is torque force, PERN by summation of R square. Now, before finding the value of F2, I'll draw the connection diagram of providing 8 bolts in each row. So let us provide 1, 2, 3, 4, 5, 6, 7, and 8. So totally 8 bolts. In the second row also, we have to provide 8 bolts. 1, 2, 3, 4, 5, 6, 7, and 8. So on a whole, we are going to provide 8 bolts in each row. Now, if you check down here, we can easily find out the center of gravity for this section. So where does center of gravity lies? Usually center of gravity lies at the center of the section. Now here we have 8 bolts. So therefore, the center of gravity lies at center of the 4th and 5th bolt. So if you consider this as first bolt, second, third, 4th, and 5th, the center of gravity lies in between 4th and 5th bolt. So we don't know exactly, but we are just assuming or considering that center of gravity lies at a distance in between the 4th and 5th bolts. Okay. Now, I said Rn. So here P value, E value that you can consider, keep it aside for time being. For let's find out the value of Rn. So Rn is the distance of extreme bolt. So Rn is the distance of extreme bolt from the center of section. From the center of section. So what is this Rn now? So from center to the extreme bolt distance. So this distance is called as Rn. So now in order to find out Rn value, let's look for these values. That is edge distance we have considered as 40. Pitch values are all 60. Okay. So the pitch values are 60 and edge distance is 40. So this is what they have said. And again, the gauge distance for ISHP section is 100 mm. So what is this gauge distance from center of the bolt to the center of the another bolt? So this value is 100 mm. Okay. Now let's find out the value of Rn. Rn is this distance, that is hypotenuse distance. So we know this distance and we also know the vertical distance. So the vertical distance and the horizontal distance we know. So in order to find the hypotenuse distance, we need to know the vertical distance and we need to know the horizontal distance. Now let's look at the horizontal distance. This distance is 50. How I am telling? Because from center of this bolt to center of this bolt is 100 mm. So I'm just considering from center of this section to center of here, the second part of the bolt. So which is 50 mm. So the vertical distance. So the vertical distance is the summation of 60 plus 60 plus 60 plus. So only from center I'm taking. So from center of bolt to the center of this bolt is 60 mm. I just need this distance, which will be 30 mm. So therefore 30. So the vertical distance will be 180 plus 30, which equals to 210 mm. So therefore Rn equals to under root 210 square. That is the vertical distance square plus horizontal distance square. So this one 50 is the horizontal distance and 210 is the vertical distance. So that's how you can find out the value of Rn. So if you solve, you will get a value around 208 mm square. 208.8 mm square. So the value of Rn will be getting approximately 215.8 mm. So this is the value of Rn. Now let's find out the value of summation R square. Okay, summation R square value. Now before finding out summation R square value, let's find out the simple concepts involved in this figure. So I'll erase all these things. You can check down later. So here, fine. Okay. Now, what is summation R square? R is the distance from center to the extreme bolts. Now, here we have 4 R values, that is 4 radial distances. R is radial distances technically. So the R value is from center to the distance of extreme bolt. So this is one value of R. Consider this as R1. Now you have another value which is from center to here, which is R2. I'll draw on this side. So from center of bolt to the center of the section, which is R2. And again, we have R3. This is R3. We have R3. And also we have the 4th radial distance, which is R4. This one. So here we have 4 radial distances from center to the extreme end of the bolt. So here we need to find out R1 value, R2, R3, and R4 values. So now let's look at how to find out the values of R1, R2, and R3. So initially, so how many number of extreme bolts are there? So if you check down very carefully, we have 4 extreme bolts. That is, this is one bolt, another bolt, the third bolt, and the fourth bolt. These are the 4 bolts which are corresponding to R1. So these are the 4 bolts which are corresponding to R1. Now how to find out this R1 value? So we have 4 bolts which are corresponding to R1. Now let's measure the vertical distance. So this vertical distance is 210 mm. Okay, 60 plus 60 plus 60 plus 30. So 210 square plus horizontal distance from here to here. The horizontal distance is 50. So this is the value corresponding to R1. Now let's find out for R2 as well. So to find out for R2 plus, now how many bolts are there corresponding to R2? This is one bolt, second bolt, third bolt, and fourth bolt. So here also we have 4 bolts. So 4 into or 4 times of, let's find out the vertical distance. So this is the vertical distance. Vertical distance is 60 plus 60 plus 30. That gives 60 plus 60 is 120 plus 30 is 150. That is 150 square. Okay. Again, the horizontal distance is 50 mm, 50 square. So this value is corresponding to R2. Similarly, we have R3 as well. So let's look for R3. So R3 bolts are 1, 2, 3, and 4. These are the 4 bolts which are corresponding to R3, radial distance 3. So 4 into R3 value will be, so you can check down from here to here. That is 60 plus 30. 60 plus 30 is 90. That is 90 square plus 50 square. Okay, 50 is again the radial distance. I mean the horizontal distance. So this is how you can find out the values of R3. Now let's look for the other value, that is R4 value. So R4 corresponding bolts are 1, 2, 3, and 4. These are the 4 bolts corresponding to R4. So we have 4. So the distance from here to here is just 30. So that is 30 square plus horizontal distance is 50. So 50 square. So if you solve for all these values, you are going to get the value of summation R square. So you'll get summation R square value as 342 400 mm square. So now you have got Rn value and summation R square value as well. So now let's substitute the values in F2 formula. So F2 equals to, we know the formula, which is PERN by summation R square. Here, P is the load. So what is the load? 300 kilonewtons. So this is the amount of load that is coming on the structure. So here you can see 300 kilonewtons. So 300 into E. E is the eccentricity of the connection. Eccentricity is 170 mm. So you can check it out. So 170, and Rn value is 215.8. 215.8 upon summation R square value is 342,400. So this is how the value of F2 can be calculated. You will get approximately 32.1 kilonewtons. So this is the value of F2. Okay. Now let's find out the resultant force. Resultant force R equals to under root F1 square plus F2 square plus 2F1 F2 cos theta. This is the formula to find out resultant force. Now we know the value of F1 and we also know the value of F2, but cos theta value we don't know. So the cos theta formula is adjacent side upon hypotenuse. So this is the formula to find out the cos theta value. Now let's find out the cos theta value. So here you can check down. So the adjacent side is, so here this is the value of theta. So the adjacent side value is 50 mm. Okay, 50 upon hypotenuse value. Hypotenuse is this distance. So what is this distance? 210 square. So 210 square plus 50 square. This is how you can calculate the value of hypotenuse. So 210 square plus 50 square. So you'll get approximately 0.232. So therefore, resultant R equals to the root of F1 square. F1 value is 18.75. 18.75 square. F2 value is 32.1 square. And 2 times of F1 is 18.75 and F2 is 32.1 into cos theta value is 0.232. So you'll get the resultant value as 40.8 kilonewtons approximately. Now, how to know whether the value which you have calculated is correct or not? Suppose this resultant force value, you have got it as 40.8 kilonewtons. So the value of resultant force must be less than the value of design strength. So let's look at what is design strength value. So we solved for design strength, which is 45.26. So the value of design strength is 45.26 kilonewtons. So here the resultant force is less than the design strength. Hence, the connection is safe. Hence, the connection is safe. Now, suppose, consider in this way. Note, if the value of resultant force is greater than VSD, then what to do? So in some cases, you will get the value of R, that is resultant force, will be greater than design strength. So in this case, what you have to do is increase the number of bolts equally in each row. So you have to increase the number of bolts equally in each row. What does this statement indicates is, suppose you have got to increase 9 bolts. So that means you have to provide 9 bolts in both the rows. So this bolt consists of 9 bolts. So 9 bolts can be increased. So how many number of bolts this row consists of? The same number of bolts the other row should consist of. Suppose 10 bolts if you are increasing. So 10 bolts should be increased in the first row and 10 bolts should be increased in the second row. So that's how you can calculate the values of resultant force. And this is how you can design the bracket connection. Now, in the end, you have to draw the diagram saying the connection details. So you can keep the heading as connection details. So how to draw the connection details? We know we have got the connection, that is the column section we have got. So this is the column section, and to this column section we are attaching a bracket plate. So this is the bracket plate, and here we have load of 300 kilonewtons, and this load is acting at an eccentricity, that is from center of the column section. This distance is 170 mm. Now, how many number of bolts we have provided? 8 bolts in each row. So 1, 2, 3, 4, 5, 6, 7, and 8. So similarly, on other side also you have to provide 8 number of bolts. So you give the notations for this. The edge distance is 40 and the pitch distances are 60. So make sure of noting down all the edge and pitch distances. Okay, and you have the gauge distance, which is 100 mm. Okay, so this is the bracket plate. This is the bracket plate, and this bracket plate is having thickness of 10 mm. So bracket plate of 10 mm thick, and this is ISHP section, that is Indian Standard Heavyweight Beam section of 200 at the rate 365.9 Newton per meter. So this is the connection details. And this is how you can solve the type 1 bracket connection design. In the next class, we'll look at the type 2 bracket connection design. Thank you.